The universe we perceive, vast and enigmatic, might be just the tip of a cosmic iceberg. What if our reality, governed by familiar laws of physics, is merely one of countless parallel universes coexisting alongside our own? This captivating notion, rooted in the bizarre realm of quantum mechanics, forms the crux of our exploration, a deep dive into the fascinating world of quantum universes. Our exploration will take us beyond the familiar, venturing into realms where the very fabric of space-time is woven from quantum threads. We'll grapple with the perplexing implications of loop quantum gravity, which envisions a universe built from tiny, indivisible chunks of space and time. Each stop on this journey will be marked by mind-bending concepts, often challenging our intuitive understanding of reality. Our journey into the heart of quantum universes begins with one of the most mind-boggling yet elegant interpretations of quantum mechanics, the many worlds interpretation. This theory, far from a mere science fiction trope, arose from the rigorous equations and perplexing paradoxes that lie at the heart of quantum physics. Everett sought to reconcile the strange behavior of quantum systems with our everyday experience of a single classical reality. The allure of the many worlds interpretation lies not just in its philosophical implications, but also in its mathematical elegance. At its core, the many worlds interpretation is deeply rooted in the fundamental equations of quantum mechanics, particularly the Schrödinger equation. This wave function, governed by the deterministic laws of quantum mechanics, encompasses all possible states of every particle and field in existence. The many worlds interpretation, if true, carries profound implications for our understanding of reality causality and even our place in the cosmos. In the many worlds view, every quantum event, no matter how small or insignificant it may seem, triggers a branching of reality. Having explored the mind-bending implications of the many worlds interpretation, we now turn our attention to a concept even grander in scope, the multiverse. The seeds of the multiverse were sown in the early 1980s with the advent of inflationary cosmology. While wildly successful in explaining many observed features of the cosmos, inflation also led to a startling prediction. Our observable universe is just a tiny pocket within a much larger, perhaps infinite expanse of space. One of the most intriguing aspects of string theory is its prediction of extra spatial dimensions beyond the three we experience. These extra dimensions, curled up at incredibly small scales, play a crucial role in determining the physical laws of our universe. This landscape, known as the string theory landscape, is estimated to contain a staggering number of potential universes, perhaps as many as 10 to the power of 500 or more. Visualizing the multiverse, a realm beyond our direct observation, poses a significant challenge. One common approach is to use the analogy of bubbles. Just as soap bubbles form and float in the air, each with its own size, shape, and color, we can imagine bubble universes scattered throughout a larger, inflating space-time. Our exploration of quantum universes now takes us on a journey beyond the familiar dimensions of space and time, venturing into a realm where reality itself might be a mind-bending illusion. This is the domain of the holographic principle, a concept so profound, so counterintuitive, that it challenges the very foundation of our understanding of the cosmos. Imagine for a moment a perfectly ordinary hologram, a two-dimensional surface that, when illuminated just right, projects a three-dimensional image. One of the fundamental tenets of quantum mechanics is that information cannot be destroyed. The holographic principle emerged as a potential resolution to this paradox, suggesting that the information that falls into a black hole isn't truly lost, but rather encoded on the black hole's event horizon. Just as the surface area of a hologram determines the amount of information it can hold, the surface area of a black hole's event horizon might encode all the information contained within it. The holographic principle, while elegant and potentially groundbreaking, is not without its challenges and profound implications. One promising avenue of research is the ADS-CFT correspondence, a remarkable duality discovered by physicist Juan Maldacena in 1997. This correspondence relates a theory of gravity in a particular type of spacetime known as anti-de Sitter ADS space to a conformal field theory, CFT, defined on its boundary, a lower dimensional spacetime without gravity. The concept of loop quantum gravity, LQG, invites us to reimagine the fabric of the universe at its most fundamental level. Unlike traditional theories that treat spacetime as a smooth continuum, LQAG proposes that spacetime is composed of finite, indivisible chunks. By reformulating general relativity using new variables known as Ashtaka variables, they paved the way for a quantum theory of gravity that does not rely on a background spacetime. Visualizing the abstract concepts of loop quantum gravity can be challenging. However, the notion of quantum foam provides a useful analogy. At the Planck scale, approximately 10 to the minus 35th meters, spacetime is theorized to be a seething, frothy mess of constantly fluctuating loops and nodes. This dynamic network forms the foundation of the universe, with each loop representing a quantized element of spacetime. While loop quantum gravity offers a promising framework for understanding quantum spacetime, it is not without its challenges. One of the primary hurdles is the problem of recovering classical spacetime from its discrete quantum structure. Another significant challenge is the unification of loop quantum gravity with the other fundamental forces and particles described by the standard model of particle physics. In the labyrinth of quantum interpretations, pilot wave theory, also known as de Broglie-Bohm theory, stands out as a bold departure from the conventional understanding of quantum mechanics. Unlike the probabilistic interpretations that dominate mainstream physics, pilot wave theory offers a deterministic and realistic picture of the quantum world. It suggests that particles, those fundamental building blocks of matter, follow well-defined trajectories guided by an invisible wave function. One of the key features that distinguishes pilot wave theory from other interpretations of quantum mechanics is its reliance on hidden variables. These hidden variables, in the context of pilot wave theory, are the initial positions of particles. These initial positions, hidden from our direct observation, act as the hidden variables that complete the description of the system. The non-local aspect of pilot wave theory is perhaps its most intriguing and controversial feature. This non-locality is most strikingly illustrated in the phenomenon of quantum entanglement, where two or more particles become correlated in such a way that their fates are intertwined even when separated by vast distances. Pilot wave theory offers a different perspective on entanglement, attributing the correlations between entangled particles to the non-local influence of the quantum potential. Our journey into the heart of quantum universes now takes us to the very edge of existence, to the moment when our universe as we know it burst forth from an inferno of energy and space-time itself was born. For decades, the prevailing cosmological model, the Big Bang theory, has provided a remarkably successful framework for understanding the evolution of our universe from a hot, dense state billions of years ago. This is where quantum loop cosmology, or QLC, enters the stage, offering a compelling alternative to the classical Big Bang singularity. QLC, an extension of loop quantum gravity to cosmological settings, suggests that the Big Bang was not the beginning of time, but rather a transition from a pre-existing state. Instead, they provide a quantum bounce, a repulsive force that halts the collapse and sets the stage for a new phase of expansion. While the concept of a quantum bounce is theoretically elegant, the ultimate test of any scientific theory lies in its ability to explain observations and make testable predictions. One promising avenue for testing QLC lies in the cosmic microwave background radiation, a treasure trove of information about the early universe. QLC predicts specific modifications to the spectrum of these fluctuations compared to the predictions of standard inflationary cosmology. Section 1. The simulation hypothesis. Are we living in a matrix? Our exploration of quantum universes now takes a detour from the well-trodden paths of physics into the realm of philosophy and thought experiments. Here we encounter a mind-bending possibility that challenges our very notion of reality itself. The simulation hypothesis. This hypothesis, far from a mere science fiction trope, has sparked serious debate among philosophers, physicists, and computer scientists, forcing us to confront the limits of our knowledge and the nature of existence itself. The simulation hypothesis, in its essence, proposes that our perceived reality is not fundamental, but rather a sophisticated simulation running on a powerful computer system created by a more advanced civilization. Just as we create increasingly realistic video games and virtual reality experiences, a sufficiently advanced civilization could create simulations indistinguishable from physical reality, at least from the perspective of the simulated beings within it. Section 2. Layers of reality, nested simulations and the nature of existence. Bostrom's trilemma pushes us to confront some unsettling possibilities. If most technologically advanced civilizations self-destruct before reaching a stage where they can create universe-scale simulations, then our own existence might be a fleeting anomaly in a cosmos otherwise devoid of intelligent life. If advanced civilizations exist but choose not to create such simulations, perhaps due to ethical considerations or a lack of interest, then our reality, while seemingly unique, might be constrained by unknown cosmic principles that limit the proliferation of simulated universes. However, the most mind-boggling possibility within Bostrom's trilemma is the third option, that we are almost certainly living in a simulation. This possibility raises a cascade of profound questions about the nature of our existence, the limits of our knowledge, and the very fabric of reality itself. Section 3. Implications and challenges testing the unthinkable. The simulation hypothesis, while captivating and thought-provoking, presents significant challenges from both a philosophical and scientific perspective. One of the primary criticisms leveled against the hypothesis is its inherent unfalsifiability. If our senses and instruments are part of the simulation, how can we ever hope to gather evidence that definitively proves or disproves our simulated nature? Any apparent glitches in the simulation could be explained away as intentional features or limitations of our perception. This lack of testability has led some critics to dismiss the simulation hypothesis as an untestable and therefore unscientific idea. Section 1. Reflections on the frontiers of reality. As we conclude our extraordinary journey through the mind-boggling landscapes of quantum universes, we are left with a sense of awe at the sheer vastness and strangeness of the cosmos. The theories we've explored, from the mind-bending many worlds interpretation to the profound implications of the holographic principle, challenge our intuitive understanding of reality, pushing us to the very edge of what we thought we knew about the universe and our place within it. Each theory we've encountered offers a unique perspective on the nature of reality, the origin of the universe, and the fundamental laws that govern our existence. Some, like the many worlds interpretation, suggest a reality far richer and stranger than we could have imagined, a reality where every quantum event spawns new branches of the universe, each with its own unique history. Section 2. The unending quest for understanding. It's important to remember that these theories, while grounded in rigorous mathematics and informed by experimental observations, remain speculative. The quest to understand the fundamental nature of reality is an ongoing journey, with each new discovery raising more questions than it answers. The lack of definitive answers, however, should not be a cause for despair, but rather an inspiration for further exploration. The very act of questioning, of pushing the boundaries of our knowledge and seeking deeper truths about the universe, is at the heart of the scientific endeavor.